So we're looking at heat transfer and heat of reaction in this section of the notes. I believe we started this problem last time, so we're going to continue on with it. But just reviewing, heat transfers from the warmer object to the colder object. So you have the object losing heat is going to be the negative side, and the object gaining heat will be the positive side. Now the reason why this works is I probably didn't go into a lot of depth about the Q part here, but the Q, you have the Q's of the two different systems, and you combine them, they end up reaching a thermal equilibrium. So they end up evening out to the same temperature. Now that's because the system you're considering, the chemicals usually are considered the system, and then everything around it is the surroundings. But heat going from the system to the surroundings where it's releasing energy, that would be exothermic, or heat going from the surroundings into the system, that would be endothermic. But, sure, go ahead. Question? I suggest you log out and log back in, or let me check my status. Maybe my status is going back. Okay, so system gains energy, absorbs energy, then we're endothermic if it's losing heat, exothermic process. So we're going to be looking at that, and then eventually most of these problems have you adding something to water and measuring the initial temperature of the water and then seeing where it ends up, and it reaches one final temperature for both objects. Okay? And usually these experiments are, conducted in the lab in like styrofoam cups where you have pretty much a good insulator, and you measure the temperature changes. Those type of experiments are called calorimetry experiments. So keep that in mind too. Those are the type of experiments where we're recording temperature changes as we're either reacting things or combining things and seeing how the heat transfers. So we have our Q equals Q here. The Q of the losing side equals the Q of the gaining side. And then we can substitute in our MCATs. So the MCAT of the losing side, the MCAT of the gaining side, they can be equal to each other because we know that magnitude of the Q, or the heat number, is going to be exactly the same. All right, so now we're looking at an example type problem here. A gold block with a mass of 125 grams was cooled and dropped into a beaker containing 200 grams of water at 25 degrees Celsius. Final temperature of the water is 22. What is the initial temperature of the gold block? The specific heat of gold here is 0.0129, which is on your table. Also, they expect you to know water. The specific heat of water, 4.184, but I'll write it up here, as we will definitely need to know that. Now, as we say here, we have our gold and our water that are going to be combined. One's going to be losing heat, the other one's going to be gaining heat, and then they reach thermal equilibrium at the same temperature. So which one's losing heat? The water is losing. The gold is gaining because the gold started out being colder than the water. So as we're setting it up, the water side is going to be on the negative side because it's losing. The gold side will be on the positive side. And you have to be very careful with your signs here because it's easy to mess it up when you're putting everything in, making sure that you have a double negative, you make it positive, all those things, because it's very easy to mess up these calculations. So watch the signs carefully. So now all we have to do is start inputting the information into the formulas. I know that I have 125 grams of my gold, so that's going to be the mass of my gold over here, like so. I know my specific heat of the gold. It's right here. when I don't know the initial temperature, don't forget delta T is the final temperature minus the initial temperature. But I do know the final temperature because as you dropped it into the water, now it has equalized thermal equilibrium. Both of them, the water and the gold, are now at, no, not 25. The final temperature was 22, right? 22 there. All right, so the final temperature 22 minus the initial temperature here. That would be in degrees Celsius. Now, over here on the water side, we have the delta T, so we have the initial the final temperature is 22 minus the initial temperature, which was 25. So watch this sign here because that's going to come out to be -3. Then we add in our specific heat, joules per grams. I'm trying to space it out right, and then the mass goes over here for the water. And the original negative side out here because this side is losing heat. So when you do the calculations, this is going to be right here, this is going to turn out to be -3, so this side actually ends up being a positive number. It's easy to mess up the signs, like I said, so be very careful as you're calculating. But the rest of it now is just a bunch of algebra to get you to solve for the initial temperature of the gold. So go ahead and take a moment, and you might have to like do a few steps in there to, you know, like this side equals this side. Do a few computations to keep it all straight. I usually do. Go ahead and take a moment to calculate that. So I usually go to like getting it to about here. Did the left side, the water side, I had all the numbers, so calculated that. You can distribute or you can not distribute on the right, whatever you choose to do. Might be easier to just divide at this point. You know, divide that out, divide this out. So, what is that number? This ends up being 155.68 equals the 22 minus TI. Then you just add the 22, or subtract the 22 from both sides? Yeah, subtract from both sides. Algebra skills being a little rusty and all. So this ends up being like 133.68 equals negative TI. So really, just change the signs or multiply both sides by -1, whatever you want to think about it as, because that will give you TI. And then TI is negative 133.68. But with all that fun algebra and stuff and narrowing it down, I would eventually, this is 3, the masses are 3, so I would just go with 3, make it negative 134 degrees Celsius. So that's pretty cold. The gold started out as being pretty cold there. And they must have had it nice deep freeze, dropping it into the water. And it lowered the temperature of the water only by 3 degrees. That tells you about that heat capacity of the water. So keep that in mind. These problems are long, but if you set them up right, usually can calculate it, and always be aware of the signs, because that's the easiest or the most frequent mistake would be messing up the signs. Apparently I didn't just the answer, so going to right here, negative 130. Go with that. That's way too many digits there. All right, for enthalpy, heat of reaction, also known as delta H. So enthalpy, or heat of reaction, is like the amount of heat per mole of reaction generated. And it can be written as a product when heat is released. If it's an exothermic reaction, it can also be written as a reactant when heat is absorbed, which then it would be endothermic. Enthalpy also can be represented separately using the positive endo or negative value exo, and it will be written right next to the equation. Remember, an energy gain, which would be absorbed by the system or the chemicals in the reaction, that is going to be endothermic, and it's positive. Energy loss, if it is being released from the system, from the chemicals, that is going to be a negative delta H. So this is how it would be written if it was in delta H form. So basically, this is the heat of reaction for magnesium hydroxide breaking down into magnesium oxide and water. This particular reaction you would have to heat up. That means this amount of energy would have to be in the reactants over here, like so. And that's what this positive delta H is telling you, that it's endothermic. So that is the amount that would need to be absorbed in for this reaction to occur, like so. So it can be written like that, or it can be written in as a reactant, like I just did. This one's showing you the combining of nitrogen monoxide and oxygen to give you nitrogen dioxide, being exothermic. And this is where they wrote the energy in as a product. But they could also have just wrote it out next to the reaction and put negative 114, like so, kilojoules. That is another way they could have written it to represent exothermic, so you know that it's a product because it has this negative sign right there. Remember, the signs really are just about like the direction the heat is going in terms of the system. If it's going into the system, it's positive. If it's leaving the system, it's considered negative, so that the signs just really denote the direction of the heat flow. These aren't too bad. It's basically like a mini conversion, somewhat like stoichiometry setup. So if we're given a reaction like this, we have iron 2 oxide plus oxygen giving you iron 3 oxide, which happens to be rust. Here they tell us the heat is being released and it's a product, so we know this is exothermic. Okay, the delta H would be negative 560.4 if they wrote it that way. But we want to calculate the amount of heat released, like it's telling us it's being released anyway, so we know it's exo, when 17.1 grams of the iron 3 oxide or the rust is being produced. So for that particular amount, this amount is for like 1 mole of the reaction, 1 time the reaction to run. When they say per mole of reaction, that's what they're talking about, because obviously the different substances in there have their own coefficients. But for 1 time of that running, it's going to generate 560.4 kilojoules of heat. But we're starting here with our 17.1 grams Fe2O3. Now, can't do anything with grams, so we should just change it to what? Moles. We got to go to moles. Let's go to moles. So grams to moles, 1 mole of Fe2O3. This is where I was saying you're going to need your periodic table, because you got to look up molar masses. So we have 2 of the iron, so that's going to be 2 times the 55.85, and then we have 3 of the oxygen, which is 16, so add all that up, and what do we get? That is correct, 159.7. Always go to 2 decimal places, it's just easier. So we all have the same molar mass. Now, that part's not the hard part, changing it to moles. This is the part where people might get confused. Because what are we going to diagonal down? The moles of the Fe2O3 go down here. Now, this measurement, this delta H, once again, is in reference to the reaction running one time. And if this reaction were to run one time, you're going to need 4 moles of the FeO, you're going to need 1 mole of the oxygen, and you're going to produce 2 moles of the Fe2O3. So that means for every 2 moles of this being produced, we're going to generate the 560.4 kilojoules. So that's how you would set it up, to convert it over to heat. Use the coefficients with the delta H for the reaction. So then we have the grams canceling and the moles canceling. And now we're going to end up with our kilojoules, which is what we want because we want the heat that's being released. So what do we get for our kilojoules? If 17.1 grams of the rest is produced, how many kilojoules are actually released in that process? Anyone? 30, that's correct. It's like 30.0 on the nose. Don't forget this has 3 significant figures here, so we're going to keep 3 in our answer. So 30 kilojoules if 17.1 grams. Now, this could be asked too from the standpoint if you reacted this many grams of FeO. In that case, it would be 4 moles to the 560.4. Or they could ask you something about the oxygen, and then that would be 1 mole of oxygen to the 560.4. So just use those coefficients, and then you can use the delta H, the kilojoules, as your conversion factor. Now for the last part, vapor pressure, boiling points, and IMFs. I know you wanted to review those IMFs. Those IMFs, those London dispersion forces, dipole, and hydrogen bonds. Actually, we're not going to review all that. We're just going to talk about these properties, vapor pressure and boiling points, and relate them to the strength of the intermolecular forces. So we kind of touched on this back in Unit 5, but adding in vapor pressure curves, because they look like this. Now we're graphing them and reading the graphs. But vapor pressure really is exerted by the gas in equilibrium with a solid or liquid. Most of the time it's liquids here, in a closed container at a given temperature. So say in my lovely water bottle here, nice closed container. Any water bottle will do. There is a small little layer on top of my water that is in equilibrium with condensing and vaporizing back and forth. It's a very thin, small, tiny little bit of gas, but that's what is going to be the vapor pressure that rests on top of the liquid. Now we know vapor pressure has to do with IMFs, because the ability to vaporize, that means it can break free from the forces that are holding it down into the liquid stage, liquid phase. Okay, so it's all about really those IMFs as to the strength, and we'll relate that to the vapor pressure and then therefore to the boiling point. Boiling points are related to the vapor pressure because in order to reach the boiling point where it will vaporize, the vapor pressure has to equal the atmospheric pressure. So we gotta have the vapor pressure equal the atmospheric pressure in order to reach the boiling point. And then it can vaporize. Now, atmospheric pressure here, these are all reading at standard pressure. And we'll talk about standard pressure again when we're talking about gas laws. But standard temperature pressure referred to the 1 mole equals to 22.4 liters. Standard pressure is still going to be the atmospheric pressure measured at sea level. And these are the values. 1 atmosphere, 101.3 kPa, 760 torr, or 760 millimeters of mercury. These are basically the same. 4 is after the guy's name, and then millimeters of mercury is the actual measurement done there. And in your phone apps, what you normally see as the atmospheric pressure, it's usually in inches mercury, because we don't use the metric system here. But if you've never noticed that, you can read in your phone app for your weather and figure out what the pressure is for the day there. And then you can convert it to millimeters if you wanted to. Now the part is that we're adding on here is reading the vapor pressure curves. And hopefully you remember from Unit 5 that things boil when the vapor pressure equals the atmospheric pressure. Well, the atmospheric pressure isn't always at sea level. You know, in the mountains of Colorado or Mount Everest or anything like that, the atmospheric pressure is much thinner up there, so you have lower pressure. So those boiling points at very high altitude are going to be also a lot lower. And that's what this curve is really representing, is at the different temperatures and the different vapor pressures, these are all the boiling points for this particular substance. Now, of course, the normal one, this is what we call the normal boiling point. Normal boiling point is at standard pressure. Like we consider room temperature like normal conditions, we also consider the pressure at sea level like normal conditions. So when we say water boils at 100 degrees, we're really referring to normal boiling point of water, which would be at 1 atmosphere. Because if you go up in the mountains of Colorado, it's going to boil, I think, at somewhere in the 90s, because the atmospheric pressure is less. So we're going to look at reading these vapor pressure curves and comparing different substances on them. But before we do that, we should really go back over IMFs and strength of them and refer to the properties. Substance has a higher vapor pressure, the molecules can evaporate more readily and escape the liquid. If it has a higher vapor pressure, that means it has weaker IMFs, weaker attractive forces holding it into the liquid phase. Now I know that this chart was in your Unit 5 steps, but I thought it'd be a good little review here. If they are strong versus if they are weak. Now volatility, being a volatile liquid, is that it evaporates usually pretty fast. So like alcohols and gasoline and some of these ones where you don't want to like leave it uncovered because it'll evaporate out. That is what a volatile liquid would be. Now, strong IMFs like water, where you don't have huge volatility, the vapor pressure is also very low, but that means it has a higher boiling point, like so. So vapor pressure, boiling point, pretty much are opposite. Vapor pressure goes down as boiling points go up, kind of an inverse relationship there. So if we're looking at the weak side of things, the weak IMFs, they're usually going to be volatile liquids like gasoline. They're going to have high vapor pressures and very low on the boiling points there, lower side. That has to do with the weaker IMFs because it's not as strong holding the molecules together. So as the intermolecular forces get stronger, more energy is required to break or overcome those forces, holding the molecules together. In other words, more energy is needed to melt or boil to change phase. So things with stronger forces have higher melting and boiling points than things that have weaker forces. So now let's reference and look at the vapor pressure curve. Once again, stronger intermolecular forces, lower vapor pressure at a given temperature, the higher the boiling point. And let's look at this graph where we're comparing water as the strongest, followed by ethanol and the diethyl ether. So here is the diethyl ether line. As you can see, its vapor pressure curve has lower temperatures at the different vapor pressures, so definitely has the weaker forces. Here is the ethyl alcohol or ethanol, the alcohol. Its normal boiling point happens to be 78.3 because that's at the atmospheric pressure, standard pressure line. And they usually mark that for you on the graph. Like here is 760 torr, which is standard pressure. So this would be the normal boiling point for the diethyl ether. This is the normal boiling point for the ethanol, and then of course water is over here at 100. And as you can see, the water curve there, the farthest to the right, means it has the higher temperatures at the different vapor pressures for the boiling points, because the line represents the boiling points along at the different vapor pressures. So now all we have to do is a few little practices here, which is graph reading, which should be pretty easy. We have chloroform, we have carbon tetrachloride, and water up here. Chloroform is this CHCl3, I believe. And then we have the carbon tetrachloride, and then we have the water there. So 3 on our curve. First 2 questions, just read the graph, very easily answered. So what is the vapor pressure at 50? All you have to do is go over here to 50 degrees, go up to the line, and approximately how much is it? 70. I put the little line there, of course, because it's an estimation, but 70 kilopascals, because this one, the pressure is being read in kilopascals. So vapor pressure of water at 70 degrees. Paying attention to our graph here, we go to the 70 mark, right about there. And that one's going to be approximately 30. Very good. Couple other little questions. What is the normal boiling point of water? So we go ahead and make sure you reference here 101.3 kPa. That is standard pressure in kilopascals. So we look here at the water, at the normal line. So that's obviously going to be 100. Very good. What is the normal boiling point of carbon tetrachloride? Here, this is more of an estimation. Looking here on this line, going down, it's right about in the middle there somewhere. Sounds like goods for 75 to me. And then they could always ask you an intermolecular force one. Which substance is the weakest or which substance is the strongest? Here it's asking you for the weakest. So out of those substances on the curve, which one's going to be the weakest in terms of forces?
CHCl3.
Yes, the CH, it's supposed to be Cl3, but I know it's really hard to see. So, but yes, because this line has the lowest boiling point, it is going to have the weakest forces. If we said which one has the strongest forces, which is the other one they could ask you, you would of course say water, because it has the higher boiling points at the different vapor pressures. Any questions? Because that's it for thermochemistry.